That's at the end. Make sure you have the handout, girls. Listening. Do we all have the handout? Yeah? I'm not going in order of the example because I just didn't like the order. We're going to start with example 26. Okay? So the very last example. So, girls, what we're learning today, we're learning sum of geometric series, but when it's infinite, so it never ends. Yesterday we looked at the sum of geometric series when there is an actual, terms, number of terms, n. Girls, this is the formula when there is no term numbers. It's just never ending, infinite. Okay? It's just basically a simplified version of what we learned yesterday. The only thing you need to be aware of is the bottom. It's 1 minus r. Okay? You're never going to have it the other way around, r minus 1. That's not the case. 1 minus r, and the ratio is always going to be less than 1. So like half, a third, and so on. So, I just thought this was a good example to start off with where we can actually use geometric sum. Because if I want to write this as a fraction, that's what the question is. Girls, this is technically this, isn't it? So 0.2, let me write down like this. So it's obviously never ending. We can actually break this down into like this. Does that make sense? Yeah? Because that's the first two, that's the next two, and so on. So using that idea if it never ends. Now to calculate the ratio, we learned that it's just the second term over the first term. And if you put this in the calculator, what you're going to get is 1 over 100. So each term, the multiplier is 1 over 100. Yep. And we know this is your A. So we can actually plug it into that formula and to get us the actual fraction for this. So S infinite is A, which is 0.23 over 1 minus the ratio, which is that. And if you actually put this in the calculator, you'll get 23 over 99. And if you type this in the calculator, you'll get that. Okay? So my point is, so what you're doing here is obviously this represents the sum of infinite number of terms. But when I say infinite, it does reach a certain limit or a certain point. That's that number. Okay? So graphically, think of it as an asymptote. See, it's like we have a graph. You know how it's never ending, right? But it is always going to approach a certain asymptote value. Think of it like that. That's what you're finding. The sum of an infinite series is like you finding what you will eventually approach as we go infinite, infinite, infinite. But it's never ending. Okay, so let's try the same thing for the next example. But just as a guide, now that you get the idea. Okay. So girls, another new word that you need to know is this is what we call convergence. When something's converging, it's reaching a certain point or a certain limit. Okay? There's infinite number of things, but it's eventually going to reach a certain limit. Okay, that's what converging means. So let's have a look at the next one, which is 57 dot. So this is obviously 0.57777 and so on. With this type of question, see how the 0.5 is not repeating? Okay? So what we want to do is just focus on the part that is repeating. Alright? So this is technically 0.5 plus what is it? What's 0.07, and the next one is 0.007, and so on. Okay? So you're just focusing on this bit. You're adding that on later after you find the sum for just that bit. Does that make sense? Yeah. So that's obviously your A, so that goes on top. One takeaway, the ratio, if you're not sure, get the second term divided by the first term, and you're going to get 1 over 10, I think. Yep, so if you plus all that, you'll get the fraction 26 over 45. And if you type this, obviously, you're going to get that. Yep, does that make sense? Sorry, can someone check there? 0.1. That's right. Yeah. All right. Now, let's get to some application of it. Let's have a look at 24 now. What I want to point from 24, girls, have a look at example 24, please. A rubber ball is dropped from a height of 20 meters. So let's say we have a 20-meter height here. We have a rubber ball that is dropped. Each time it strikes the ground, it rebounds to 3/4 of the height. So when it goes down, it goes back up to about 3/4 of the height, and then when it goes down again, it goes to 3/4 of the previous height, and so on. Does that make sense? That's a question. Now, here's the thing though. It doesn't say the number of terms. So that's when you know you've got to use the infinite sum. Yeah? It doesn't say how many times you'll bounce. It just says find the total of numbers of meters it travels, given that. So, yeah. So consider this as actually your first initial height. Okay? The ratio is obviously 3/4, and then you just got to plug it into the formula. Okay? It's not hard. So 20/1 take away 3/4, and eventually the amount of distance it travels will be 60 meters. Okay? Any questions so far? All right, last example. All right. Girls, this one's a bit of a tricky question. It looks tricky, but we've got to understand the definition of this. Find the values of x for which the series converges. So I briefly mentioned what converges means. Girls, the question isn't find the sum. That's not what it says. It says find the value of x where it converges. So when it says when it converges, it means, what does it mean again? It reaches, so the sum, when it converges, the sum of these infinite series reaches a certain limit. Okay? Now, here's the condition for something to be infinite. That, right there. The ratio has to be less than 1. So that's what you've got to work with to prove or to make this converging. So in other words, girls, the ratio is, what's the ratio? What's it going up by? Look at the powers.
X minus 3.
Squared. Yeah? So for this to work, basically that needs to be less than 1. Okay? So basically, you're just solving that. Alright? So if you solve this, girls, I'll do the work here. I'll just expand it out. X squared minus 6x plus 9. X squared minus 6x plus 8. Factorize this bit out. You're going to get x minus 4. X minus 2 has to be less than 0. Now from here though, we've got to get the inequality correct, going back to year 11. So this is obviously x equals to 4, x equals to 2. So I like to do it graphically. So we've got 2, and then 4. It's obviously a parabola. If it's less than 0, which portion of the graph are we looking at? Above or below the x-axis? Below, yeah? So that means all the values here are just basically this. It's in between 2 and 4. Yeah, remember that from year 11? Whereas if it was above, we would have to write this bit here is greater than 4, this bit here is less than 2. Yeah? So it just depends on the inequality. So that's your answer for that to be converging. You just got to use this condition. Does that make sense? All right, girls, that's it from me basically. I want you to try for this exercise, I think every odd question, I think. Was it even or odd I want you guys to do? Try every odd questions, okay? All right, thanks girls, that's it from me. Oh no, not yet. Hold on, not yet. Let me just write it out first. Okay. Girls, a question has been raised yesterday.
For example 24, why did you just leave it at 16? Because the answers have something to do. They added 60 to 80.
Oh, sorry. Wait, total distance. Oh, sorry, I forgot to put. Thank you. Because when it drops, it travels at 20 meters as well.
What? But they did 15. They did 60 plus 80 equals 140.
Wait. Oops, sorry. Thanks for looking at it. What did I miss? Hold on. Oh, they gotta do both. Wait, this equals to 80? Sorry, I wrote that wrong. That equals to 80? Oh, that's tricky. Oops, sorry girls. I missed it. So, alright. Okay, my bad. Girls, this distance is when it goes down. Okay, so what this represents is actually all the down motion early. Okay, we forgot to count in the upward motion when it goes back up. So this bit, okay, that's another geometric series separately. But what's my A though? 15. Do we know why that's 15?
It's 3/4 of 20.
Yeah, this is 15 because 3/4 of it for the upward motion. Yep, so that's 15 here. One takeaway, it's still 3/4. Sorry girls, that's for downward motion, upward motion. So the total is, yeah, that plus that, which is 140. Yeah. Because it's always going to go down and up and down by 3/4. That's the question in the given. It says each time it strikes the ground, it rebounds to 3/4 of the height. Okay, that will never change. Yeah, thanks for that, girls. Okay, yeah, I missed that. Now, last thing. A good question has been raised yesterday. So I've got two examples here for you. So in your test, you know that formula, and you know how I got confused on whether to substitute the actual score for the x or the z scores. Yeah, here's what I got. If you get that formula in particular, it comes in only two forms. If you get that one, you put in the raw score. And an extra way to confirm that is look at how they introduce the formula. What does it say after that? The adult wingspan, blah, 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 is normally distributed with a mean of 180 centimeters and standard deviation of 12. It's not mean of 0 and standard deviation of like +3, -3, plus or minus 1, that kind of stuff. So if they give you that particular formula, and then on top of that, it confirms it by giving you the actual raw score, substitute the raw score. In comparison to the next one here, come on, where is it? This one, if it's that formula, do you see the difference? In the first one, we had that sigma sign. This one is without the sigma. You substitute the z score. And we can confirm that by looking at the next line. How do they introduce that formula? Is a normal probability density function with a mean 0, standard deviation 1. Do you see the difference? That's when you substitute the z score. Does that make sense? Yeah, so I'll show you the other formula again. So that's for the z-score substitution. This is for the raw score substitution with the sigma. And to confirm it, look at how they introduce the formula. They give you the actual raw score, not the z-score. So as soon as they say mean of some number, use a raw score. If they give you the mean with 0 with that formula, substitute the z-score.